So as usual, now you all get a little notice saying you're getting recorded. And I am getting it too on both my phone and my tablet. Got it. And we have someone to let in. Okay, so right. So today we're going to talk about exploratory data analysis, which is all stuff that, depending on who taught you stats, this is stuff that you would have run into before. I know if I taught you, you had something very similar to this. In fact, you might have had almost exactly the same slides in 2126. And I think Dwayne uses similar slides as well. Like that animation, pretty great, right? So if you're going to find anything out about a data set, first you have to understand the data. Now that obviously seems like a bit of a tautology, but in fact, it's the case that you have to get a feel for your numbers. And that's what, move my mouse pointer off there. That's what this is all about. It's getting a feel for a data set. And if you have a feel for the data set, before you do any inferential procedures, before you do any t-tests, ANOVAs, regression, you have to know what the numbers are going to tell you. My PhD advisor used to always say that statistics is there to prove what you already know. You should be able to look at your data and go, oh, I know what happened here. So basically, as I said, this is getting a feel for your numbers. It's easier to find any mistakes this way. It's easier to guess what actually happened. Right now, you don't know for sure. You can't confirm this without doing some kind of inferential procedure, but you can get a pretty good idea about what happened. And finally, you're going to find some odd values now and then. So sometimes you're going to find something that just doesn't make sense, right? One of the data sets that I've used over the years in assignments, in fact, it was given to me as an assignment, and then later on it was used, I used it for an assignment, was a data set looking at people's smoking behavior. It was collected by an old friend of mine, and he was looking at, as I said, people's smoking behavior and trying to predict how many cigarettes people smoke a day purely with behavioral measures, which is very useful because you normally do that with physiological measures, which are somewhat invasive. Anyway, one of the things he asked people is how many, of course, the target variable, which is trying to predict how many cigarettes do you smoke a day? And one person said 400. You can't smoke 400 cigarettes in a day. Well, you probably could, you'd be dead in a week. Because you would have coughed up all of your lung. So that's obviously a mistake. Probably coded wrong. It's probably 40. Another person said they've been smoking since they were 4. Now, when you look at that, you think to yourself, do they mean 14? Maybe, but you don't know that. Maybe at that point you go, I don't think I want to include that person's data because that's a different set of people. That's not your standard smoker. That's your professional, screw the Olympics, go pro level smoker. So it's probably the case that you would want to take those data out. So you'll be able to find these weird little situations, these weird little things that sometimes people call outliers, and remove them. Okay. So that's just a couple of reasons you want to do this. So one of the most important and overlooked parts, in fact, of statistics in general is exploratory data analysis, or EDA. The reason this is overlooked is people want to know, oh, do I have a significant effect? Oh, do I have a significant effect? So they don't know if they have one or not. So what they end up doing is they do that instead of looking at their numbers first. So this is something that was developed by a guy named John Tukey. Tukey was I think he's probably dead by now. Gee, I'm going to put this on YouTube and then maybe get a comment from John Tukey saying I'm still alive. Pretty sure he's gone. But anyway, Tukey developed these techniques, really not developed so much as put them all together and legitimize them, because Tukey also did a lot of important things in inferential statistics. So this allows you to generate hypotheses and to get just a general feel for your data. And as much as I'm, a scientist, and I don't worry much about feelings, having an intuitive feeling for your data set really is important. It really is important. Right. Okay, any questions I can answer so far? You good? All right. So you get an idea of how an experiment ran, but you haven't lost any richness in your data. So you don't want to lose what's called the richness in your data. In other words, you want to still be able to see all of the possible numbers, right? You want to see all the numbers. Oh, died July 26, 2000. Okay, no chance that John Tukey, thank you, Evan. There's no chance that John Tukey will be comment. If he does comment on YouTube, oh, that would be impressive. From beyond the graves, that would be pretty cool. Thanks, now I know. Yeah, so just get this idea of how things are going. So I got some numbers here. These numbers don't matter. In fact, I don't even know what they are. Well, I know they're numbers, but let's pretend that they look like, let's pretend it's out of 35, a test. And this is, I don't know, let's pretend this is a group of, well, let's say it's a group of stats students, okay? And this is, they've taken a test, short little test. It's out of 35. I think your second test is out of 40. So this could be very similar to your second test. Fine. So we have people on the X, the value, that's the people, we got the frequency is 1. So we got one person got 10, 2 people got 23, 5 people got 25. This, in fact, looks a lot like if it was 2126, not 3256, what you get, because you get some people who are just completely in trouble, like we have here. And then we have a couple people who are almost perfect or actually perfect, right? This is not an uncommon distribution for, well, for any test, really. When you look at those numbers, the first thing you might jump out at you is we have somebody who's really in trouble. 10 out of 35 is not good, right? Did that person get 10 because they didn't know the material? Well, clearly. But did they get 10 because they didn't study? Did they get 10 because they just don't get it? Did they get 10 because they're actually in the wrong class? I don't know about you, but in my first year, I walked into a 4th year chemistry class and sat through it because I was so embarrassed that I sat in the wrong classroom. That actually happened. I'll also say that, you know, looking back, I don't think anybody would have cared, but it's your first day, your first day of first year. What do I do? So, you know, you get all concerned. And that did actually happen to me. So here's some numbers. Let's try to do something with this. First of all, you can get an idea here that we have a peak of some sort around 25. What else could we say? It's pretty symmetrical, right? Isn't it? I mean, we got a peak at 5. We got a couple of 2s on either side, though 23 is a lot further from or closer to 25 than 30 is to 25. Okay. But it's symmetrical-ish, if that's a word. So we can talk already about some stuff. So what we can do is make a frequency, that frequency table allows us to do a couple of things. One of the things we can do is it's easy then with a frequency table to get a total. This is the total score, everybody's score all put together. That's the sum of the X's. Remember what the X's are, that's the scores, times their frequencies, right? The sum of X times F. So if you add all these together, 10 times 1, 23 times 2, 25 times 5, 3 times 10, 23 times 1, you add all that together, and you end up with 309, assuming I did the arithmetic properly. Now you're saying, Dave, I would do this with a computer. Yeah, you might actually, but you know, that's quick enough with arithmetic. You could do it by hand or in your head, right? So maybe you do. Now this, you might think yourself, which I think I keep saying, why is this useful? Well, this might be useful because we can use the total to get things like averages, right? To get the mean, stuff like that. One of the things you can also do with just a frequency table is you can make what's called a relative frequency histogram. There's one. Now, did I care about the what do you call it? The scale? Obviously not. If you take a look here, there's 3.75. You can't have a frequency of 3.75. We said these are people. There's no such thing as 0.75 of a person. I just threw this into, what software do we use to do this? Oh, it was the Mac program Numbers. And I just said, make a relative frequency histogram. and it made one, because this, I'm not using this to present anything in a paper or at a conference. This is for me. So I look at this, and in fact, I'll let you a little bit behind the fourth wall here. When I give quizzes, assignments, tests, essays, final grades, I actually do this with all of them, because I just want to take a look and see, is there anything weird going on in this class? Yeah, if I looked at that, maybe there is something weird going on, right? I've lost no richness in my data, and it's easy for me to reconstruct my data set. I can tell you exactly what the numbers are. Now, it's not totally easy because the scale is kind of screwy, but I can pretty much tell you just by looking at this. Well, I know the answer to this, obviously, but that one person got 10, 5 people got 25, except one person got perfect, one person got, was that 34, 33, whatever it was. So I can give you, I have a pretty good idea of what happened in an experiment, in this, I keep wanting to say experiment, this is an experiment, but what happened with these data just by looking at this thing. And I can reconstruct the data. So that because I can reconstruct it, I've lost no richness in the data. It's all still there. So I can spot oddities. And the first oddity, and like I said, is this guy here, this, or woman, just this person here. What the hell's going on there? And I don't know the answer to that question, but that would allow me to go look. So when I do this for my classes, I would go look and say, okay, who got 10 out of 35? And let's say it's a stats class, right? Because that's what we said this was. And if I look at that, I would then look and see, when did they, what year is the person in, right? I would see things like, have they taken any other classes with me? Is this a typical kind of mark, which it wouldn't be for people typically in a course like this, right? Because you're all in at least third year and you're in the honors program. So it would concern me, and I would look at it. I would also look at the person who got 35 and say, oh, who's this? Maybe I'll keep an eye on this person. Right? So I can spot odd things. Perfect on a stats test isn't odd. 10 out of 35 is odd. And in fact, think about this. If you just covered up, maybe I can do that with where's my pen here? If you just covered up, where are you? Come on, there you go. So let me just pull this up here. Let's use black. No, let's not use black. Let's use blue. No, let's not use blue. That's stupid. The writing's in blue. Let's go with red. So let's pretend that's not there. Oh, that doesn't look weird at all now, does it? It looks completely fine. If you looked at that, if your prof said, here's a distribution of the marks in the class, and you had this, you would go, oh, cool. So this tells me that this person here is almost maybe from a different population. Maybe they, like I said, maybe they actually aren't in the class. Maybe there's somebody who's taking this course because, and this doesn't happen very often because there's a lot of prerequisites for this class, but there are other classes I've taught where it's like a third year advanced psych class or biology class, and you say, dude, why are you in this class? And it's like, oh, it's the only course I could fit in my schedule, and they waive the prerequisites, and then I want to know who they are. But that does happen. Usually a 10 out of, you know what that usually means? Somebody had a bad day. So you see that little trick I just did there? I was able to cover one thing up. It's not really much of a trick. Yeah, I'm basically like Penn and Teller. Quite a trick. Watch this one. You've ever seen this one? It's pretty good, right? So you're basically looking at this and saying, I can find out, I can get an idea of what happened, and I haven't lost any richness in the data. And this is the kind of thing you do with data when you actually deal with what you're supposed to do. Well, not everybody does it. The first thing I tell my honors students when they're collecting data for their thesis, and they get all excited, I said, just show me some graphs. Don't show me any t-tests. I don't see any analysis of variance. Show me some freaking graphs. What happened? Right? Okay, any questions I can answer right now? Okay, that was really just a place for me to have some coffee. Now, we don't always have numerical data. Sometimes we have categorical data. So you don't get a histogram here. It's similar. You get a bar graph. You know what? I'm never going to ask you what's a histogram or what's a bar graph on a quiz. It's not 2126. Okay. You know, pie chart too. I hate pie charts. They make no sense to me. I shouldn't say no sense. They make much less sense to me than relative frequency histograms or any kind of bar graph. So with categorical data, the x-axis has categories on it. And where they are on the chart has no bearing on anything. It means literally nothing. Literally nothing. Parks and Rec, anybody? So there's no scale. So if you had like different hair color, you know, brown, red, blonde, black, it's your basic four. You wouldn't, it doesn't matter where you put them, right? Because one isn't more hairish than another. So let's say we have stats 2126. This is a pretty, not an uncommon distribution. In fact, this was taken from when I first made this slide up, which was in 2006. This actually was in my 2126 class this time. So I had 38 psych majors, 15 sociology. They don't take 2126 anymore. 18 CESD, they don't take it anymore. And biology have their own stats class now. So usually now it's all psych students, or almost completely. It's usually a few geography people. And sometimes there's the odd person from business because they're it doesn't matter. Why am I telling you this? But let's just say this is our distribution. So what do? We can graph it like this. And again, all I did was I told numbers, in this case, it could be Excel, could be Google Sheets, doesn't matter what. I just said, just do a thing. Make me a relative frequency histogram. Right? Or sorry, a bar graph in this case. And it did. Now, as I said, along here, where I can use this, it's nice, I can use this as a pointer when I keep in mind that it does, I don't want to block things out. Notice the size of my pointer. You know why? Because I can't see. Okay. This doesn't mean anything. I mean, does it make any sense to say that we have psychology here because it's less of a discipline than sociology, which is less than no. And if we're going to start that, we should be over here because we're better, right? So where these things are positioned doesn't matter. This is something you really have to be cognizant of when you're looking at data. It can implicitly bias you to things depending on where things are, where categories are put on an x-axis. It really can. So be careful with that. Here's a pie chart just for comparison. It does nothing for me. I mean, I can tell you by looking at that the majority of students are psych students, but it doesn't do anything for me. If it does for you, use it. These are always, you're using them for yourself. I have literally never in my career read a paper or seen a conference presentation using a pie chart in the kind of psychology I do. Never, not once. Now, other people use it and they love it. They're all for it. Great. Use a pie chart if you like them. I wouldn't put it in a paper. In fact, I bet if you put it in a paper, you'd get the following review. Could you do that as like a graph, like instead of a pie chart? Because pie charts suck. Right? Whenever I see pie charts, I think of, well, let's look at our projections for this quarter's sales, blah, 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 the deliverable vertical integration and various other business bullshit speak. So, all right, good so far? Again, I think you've seen this stuff before. But if you have questions, ask them. All right. So we have quantitative variables we use as the histogram. Quantitative just means they have quantity. What we can do with quantitative variables and a histogram is we can actually see central tendency. So, and we can see the spread, how spread out the numbers are, and we can see the shape. Really, these three qualities of a distribution of a batch of numbers allow us to really describe a batch of numbers well. Central tendency, basically average. Spread outedness, how spread out the numbers are, and the shape of the distribution. with that, we can even eventually compare distributions, which basically is what this whole course ends up being about anyway. All right. There are ways we can describe shape. By the way, I'm not ever going to get into this other than say that these are words that you probably should know the meanings of, but that's about it. So you have skewness. Now, skewness, which is a weird word, right? Something can either be skewed to the left, that's here, or skewed to the right, here. And you're saying to yourself, but that looks like it should be, that this one here should be skewed to the right and this would be skewed to the left. Yes, I agree. However, that's not, like intuitively, that's what it should say. That's not right. Here's a way to keep track of that from a former colleague, a now retired colleague, Cheryl Reed Elder, who once told me, the tail tells the tale, which is the only cutesy expression in all of statistics. So here it is. There's the tail. There's the tail. It's skewed to the left or negatively skewed, skewed to the right or positively skewed. All right.
Sir, is there a difference from saying it's skewed to the left versus saying it's skewed at the left?
Don't think so. But I've never
Okay.
heard. I've never heard at though. So there may be, but I don't think there probably is. That's wild. Basically, skew. For me, the important point is this: skew. When something is skewed, a distribution is skewed. All it means is it's not. It's bunched over to one side or the other. So people talk about skewness a lot. It's funny. In the last 10 years, people have become more interested in statistics for a few reasons. I think one of them is that election prediction sites. So you got things like 538 and 338 and things like that, where they predict elections, and they talk a lot about data and those things. And there's also, oddly, the rise of advanced analytics in major professional sports, in soccer, hockey, football, basketball, baseball especially. So people talk about sample size and skewness and not really knowing what those words mean. Skewness just means it's the data are bunched in a weird way, and they're not symmetrical. So sometimes you'll say, well, you'll hear people say, well, that's the sample is skewed. And I usually look at them and go, how? And they go, well, I don't know what that really means, but I heard a guy say it. I read a thing on a blog. So it's funny how these terms have become popular. Whoops, this doesn't want to play. Okay, we'll have to do it through here. That's all. That's fine. Stupid machine. All right. Then there's kurtosis, which sounds like an outpatient thing. They can cure something. They can cure outpatient nowadays. A leptokurtic distribution. I always note how I'm looking down and reading this. I don't remember what this means. Kurtosis is about how peaked something is, but I can never keep in mind what. I don't have a mnemonic like the tail tells the tale for this. Leptokurtic means peaked, and platykurtic means flat. So leptokurtic is like me, platykurtic is like Paul Dupuis. See, it's a little joke because Paul's huge. So actually, I think he's lost some weight. Somebody told me. I don't know. I'm still going to call him, make fun of him. He makes fun of me. You guys have to understand we're friends and we make fun of each other. It's not. Why isn't this? I guess I won't worry about the remote right now. Except maybe I want to, though. That's really annoying. I see. What's it say here? Wait, there we go. Oh, good. It's back. See, I have one iPad here that I have the presentation running on that's being shown here. I have another iPad that I'm on Zoom on, and then I have my phone that I'm on Zoom. Anyway, good. So a little bit more on shape. A distribution, of course, can be symmetrical or asymmetrical. It can also be unimodal or bimodal, right? So you think about like a unimodal distribution. Let's draw a quick picture. A unimodal distribution will look something like that. Might look like that. That's every time I draw a distribution, they always end up being sort of slanted. That's meant to be symmetrical. A bimodal distribution would look something like that. Whoops. Yeah, it's close enough. Again, it should be symmetrical. In fact, oftentimes, let's just erase that one. Let me show you what the distribution of scores looks like in intro psych after their first test. Remember your first test in intro psych? Because that was almost always your first test you took in university. The distribution looks like this. It's almost exact. There are people who get it, or at least kind of get it, and people who think they're still in high school. So that happens a lot. Usually these people here end up moving over here, but it's certainly the case that you often end up with a bimodal distribution. You do in 2126 intro stats too. Eventually those people all move over to getting it. That's almost always what happens. You could get a uniform distribution. What's a uniform distribution? Well, looks something like, oops, let's erase some of these. Okay, a uniform distribution looks something like this. So there's the graph, and it's like that. So every possible value is exactly as likely as every other possible value. When does this happen? It doesn't happen with tests and quizzes. But if you think about, let's, instead of making this a straight line, let's try this again. And we went 1, 2, 3, 4, 5, 6. Probability there's 1 out of 6. That's the uniform distribution. Those are die rolls, right? Each side is equally likely to come up. Or a great one here would be like that, and just heads and tails, and it's 0.5. Right? So those are uniform distributions. They're not important. We don't get them a lot with data we collect. They usually tend to be more theoretical things and things with, dice rather, coins, etc. All right, so here's an example. This is my favorite example because Mario is probably my favorite hockey player of all time. A little bit about Mario Lemieux. Mario scored a lot of goals. Mario might be the best natural goal scorer in the history of hockey. There he is after Canada won the 2002 Olympics. And as a way of looking at things, a benchmark in professional hockey is scoring 50 goals in a year. The most goals ever scored in a year is 92. He didn't do that, but he got to, you can see 85 here. A couple things about him. He also had, he now owns, well, he's just in the process of selling, but he actually owns the team he used to play for. They were losing a lot of money and they owed him a bunch of money after he retired. So he said, just give me the team then. So he owns the Pittsburgh Penguins where he played. And he ended up, he quit because his back was really bad and he was injured. So he stopped playing. And then in 2005 or 2003, I'm sorry, or 2002, something like that, he decided to come back. Yeah, 2002. And he did. And he had retired and he was still the best player in the world at that point, but he hadn't played. He also lost, you might look at these numbers and go, there's something weird going on. Why does he have like that? He's 18 years old here, scoring 43 goals, 48 goals, 54, 70. This is 85. This is in 1987. And then you have these weird years like 6. What's going on here? This is a weird one here. 17. You might think, what's going on there? 19. Oh, at one point he had cancer and he was out for 6 weeks. He still won the scoring title. Excuse me. So Mario was a hell of a hockey player. He's probably my favorite non-Montreal Canadian player. Those are pretty impressive goal numbers. So a histogram would be a good start, but you might want to group the values here. So a histogram is a good start. We could easily do a histogram, but we've got, how many times do you score the same number of goals in a season? Do we have any times? 43, 54, 45? Not really. So maybe we want to do something with this. So there is a histogram. What are these? What's with the 90? Well, that's from 85 to 95, right? And it's sort of 85 to 94. That's what the limits are. of that graph. It's not something to get too concerned about, because this, again, all you're doing here, I just threw these into Keynote, or not Keynote, numbers, and just said, make me a graph, and it made me a graph. And it did the grouping. But when I get this, I've lost richness. Now I don't know what some of the numbers are, because these bins here of like, say 5 to 14 or whatever, 85 to 94, those bins are 10 goals wide. So I've lost some richness in my data, right? The real limits, by the way, are 84.5 to 94.5. If you're into that kind of thing, don't worry about that too much. That's just because no one can score half a goal. That's why technically that's what they are. Okay. So you have to make sure the scale makes sense here, especially on the y-axis. Let's just quickly go back. Whoops. Can I go back easily here? No, it doesn't want to let me. Okay, let's try. Okay, yeah, I can. So let's go back. Now let's take a quick look at the y-axis. We have 3.75 as one of the values. Again, that's simply because I just told the computer to make me a graph. So when I see 3.75, 1.25, I know no one can score. There are no quarter seasons. 0.75 of a season doesn't make any sense, right? But I had the computer just do it automatically. The computer doesn't know their goals, right? So instead, we have to just be careful about our y-axis. Make sure our y-axis makes sense. Our scale makes sense. The scale's okay here. The values are a little bit wonky, but the scale's okay. The scale's okay. But you can easily use a scale, as I say here, especially the y-axis, is if the y-axis scale doesn't make any sense, you can end up with, you can mislead people. So here's something, let's just go back so I get some clear space here. So if I showed you a graph that looked like this, or a histogram look like that. Okay. What do you think immediately? You think, ooh, this is huge. What the difference here? This is it's like, what is that, 5 or 6 times bigger, you think, right? Huh. Then and let's say I'm not even lying about these numbers. But if this is 50, 51, 52, 53, 50, this is 55. Right? So 55 at the top, 50 at the bottom. So this is not a real origin point here. This is not 0, 0, which we would normally think of it. This is 50. This looks way, way, way bigger, but it's not. Always look at graphs, especially when they're coming in ads, when you see them, oh my God, political campaigns, and every party does this, by the way. Some parties are more guilty than others, but every political party in Canada does this. They make these bullshit graphs, and you look at them, and you have to look closely at the y-axis. It's an important thing. I'd love to see in a debate someone get called out for using a shitty graph. So you have to keep an eye on that. Like I said, in advertising, especially political advertising, because it's not as regulated as regular advertising. One of the problems of the histogram, of course, it's group data, so you lose some of the richness. We've talked about that already. So it wouldn't be a huge deal here because we have, I don't know how many years we had there, 13 or 15 years. That's not a huge deal. But what if you have 200 data points? Well, you might want to use something different. Here's the stem and leaf plot, which is a bit of a dumb name, but here's a stem and leaf plot. You can see what we've done here in the stem and leaf. We've got, I keep pointing at it with my hand and I should be using my pointer. He's got a year with 1 goal, a year with 6 goals, a year with 7, a year with 17, 19, 28, 35, 43, 44, 45, 48, etc. Okay, you see how that works? And this is called an ordered stem and leaf because the leaves, these are the stems, These are the leaves. Yeah, okay. So on the left are the stems, and then you get the leaves coming off of them. I think somebody tried to come up with a cutesy name. It's a stupid name, but whatever. So it's ordered. So this is an ordered stem and leaf plot. You interpret this just the same way you interpret a histogram. Okay. You interpret this exactly how you interpret a histogram. It's easy to spot outliers. I don't know why I have it spelled like that. It's spot. Are there any outliers here? Well, all these years here where he's got like 1 goal, 6 goals, 7 goals, 17 and 19 are even a little bit weird. Those are years where he was injured. Mario got injured a lot. So he had non-Hodgkin's lymphoma, and he was only out for 6 weeks to still win the scoring title. Explain that to me. He had horrible back problems all his career. So if you look at all that, you might say it's almost like that's a different player than this player here. This player here is one of the finest players ever to lace up skates. This guy here is pretty amazing, but he can't do what his body wants to do. And it preserves all the data. We can get them all back. Assuming I copied this properly, we can get all the numbers back. And it's easy to spot the 50th percentile, which is the middle number. So how many numbers do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it's going to be the 9th number, because the 9th number is going to have, right? The 9th number, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to have 8 on one side and 8 on the other. It's a balancing point. It's right in the middle. It's 50-50. In this case, then it's 44. That's the 50th percentile. 50% of the scores are here and below. 50% of the scores are here and above. So you have to do any quick calculation here. All you have to do is do a stem and leaf plot and count. And I imagine you can all count. Now, usually, you know what? A computer can do a stem and leaf plot for you. SPSS can do it. By the way, there's a video on my website at davebrodbeck.com now, but setting up a data set with SPSS, and it works the same with PSPP. For those of you who had to use PSPP, if you have, say, a Chromebook or something, they'll both work. So you can play around. In fact, I think I used the Mario Lemieux goal total here in that video. In fact, I'm certain I used it. All right. So what you can get from the stem and leaf plot is a thing called the 5-number summary. Okay, the 5-number summary. You can get the first quartile. What's a quartile? It's the median of the first 50%. So it's the 25th percentile. The third quartile, which is 54. So the quartile is just 25th and 75th percentiles. So halfway between the minimum and the median, and the median and the maximum. So 19 and 54. Let's go back. So right there, that's the median. So that's 9 numbers in. 1, 2, 3, 4, 5. 1, 2, 3, 4. There's 19. 1, 2, 3, 4, 5. 1, 2. Oh, sorry. 1, 2, 3, 4, 5. Yeah, 54 and 19. So, you know, you can actually calculate those things with there are formulas people use, but you can also just count, which is way easier. You know, I can do arithmetic in my head really well, but I also am able to count on my fingers. Like, it's not like it's a bad thing. I don't know why we have this notion that doing something simple is bad. So that's halfway between the minimum and the median and the maximum. And I think you know what the words minimum and maximum mean, so I'm not going to define those. Wait, I said, oh, it's coming up all at once. Who cares? Well, there's 5 numbers. The minimum is 1 and the maximum is 85, which gives you the range, which you might report as either 84, 85 minus 1, or 1 to 85. 1 to 85 is probably better because it gives you a pretty good idea of what it still tells you what the minimum and the maximum are. So the range is 84. The minimum's 1, the maximum's 85. Median's 44. Let's see if I can remember this. The first quartile's 19 and the third quartile's 54. When you take those 5 numbers, you can make something called a box and whisker plot. God, the names are stupid. I'm almost embarrassed saying them. You go to a restaurant, you have to order something that's got a stupid name. Yeah, I'll have the big, fun, jumpy, happy burger. No, I'll have a burger, thanks. The big, jumpy, fun burger coming to you soon from McDonald's. So you got a box plot. I call it a box plot. Box and whisker plot's a weird thing. This gives you an idea of the shape of your data. So let's take a look at, oh, look, how did I do that? SPSS, I just put the numbers in. Hey, there's one. So that's just a screenshot copied from SPSS. But any decent piece of stats software will do this. There's all kinds of good stuff out there. PSPP, JASP is another one, JASP. It's a little different. We're going to use SPSS in this course, but you don't have to. You can also do it in a very roundabout way in Excel, in a very roundabout way in Keynote, and a very roundabout way in Google Sheets, to the point where you have to watch like 3 or 4 YouTube videos and it's a nightmare. So I just use real stats software here. What do we have though? Well, there's your median. Okay. There's your minimum. There's your maximum. There's your third quartile. There's your first quartile. So you take the first and third quartiles and you draw a box. Then you draw in the median. And then you go from the median out to here. And what we have here is the distance from the third quartile to the first quartile is called the interquartile distance, the IQD, or the interquartile range. You then take that number, multiply it times 1.5, and go from the median up to here and the median down to here. That's one way to do it. The other way some people do is just, and this might have done it this way, is just go to the minimum and the maximum. If you use the 1.5, which I think, what did this do there? No, this used 1.5. So we take this amount here from Q3 to Q1. We multiply that times 1.5, and then we draw from the median up and from the median down, and we get the interquartile. We throw that in there, and then if you have any numbers that are above or below, a lot of people just say immediately those are outliers. You know, the nice thing is you just do this with a computer. You don't have to remember exactly how to do it. See, at this point, I've run out of titles, so I just like, and it continues. I don't know what to say. All right, so we talked a little bit about the central tendency, right, at the very beginning. It's one of 3 properties necessary to describe a distribution. We've talked a little bit about shape here, all that kurtosis and stuff, right? Here's an example. So let's consider the following batch of numbers: 1, 5, 9, 20, 30. They're just numbers. I don't know where they came from. They don't know where they came from. They are just numbers. And here's another batch of numbers: 11, 12, 13, 14, 15. Just 5 numbers. I picked them for a reason, but they're just 5 numbers. Both have the same mean. You know, they will sum to 85, you divide by 5, that's 80. So sorry, 65. 65 divided by 5 is 13. So the mean is 13 for both of these batches of numbers. Right? So you see what I did there? All I did is I summed them. So 1 and 5 is 6, and 9 is 15, and 20 is 35, and 30 is 65 divided by 5 is 13. Okay. So it's just it's the same. It's what you're used to for both of these. Let's turn that on. So it's 65 over 13, which equals, sorry, let's fix that. 65 over 5, which equals 13. So the mean for both of those is 13. The mean for both is 13, right? Right. They're clearly different numbers, Like, obviously, they're clearly different. So they're the same, but they're different. 1, 5, 9, 20, 30, and 11, 12, 13, 14, 15. So they both have the same mean, and they're both symmetrical, right? They really are. There's as much on one side as the other. They're basically uniform distributions of 5 points. How are they different? Well, one's more spread out than the other, right? Yeah. The top one here is much more spread out than this one here. So it's much more spread out. So what we need then is a measure of spread outedness. We need a measure of spread outedness. Okay. Well, let's do that. Well, how are we going to measure that? Well, there's a few ways. We could start with the range. It's extremely crude, the range, but we could start there. So 1 to 30 versus 11 to 15. Okay. So one has we could say of 29, the other one's 4. That gives us some idea. It's some idea. It's a little crude, but okay. We could look at the interquartile distances. Sure, I guess we could. It's still pretty crude. The interquartile distances, let's go back here and we'll take a quick look. Whoops. So the first, well, let's see, for the top one, that's the median is 9, and the median here is 13. So the first quartile is 5 here and 20. Remember, it's just halfway between the median and the maximum, the median and the minimum. 13. Okay, so 2 and 2. Okay, that gives us some idea. You know, IQD is like, so it's 14 to 12, it's 2, 20 to 5, 20 minus 5 is 15. Okay, again, this tells us this one's more spread out than this one, but it still seems very crude to me. The range is a start. The IQD is the next thing you could do. It's still pretty crude. It's still pretty crude. It doesn't really tell you a great deal. It tells you something. There's nothing wrong with it, but it's not giving you enough information. Right? So it's not telling me enough. I need more. I need more. So we need something better. Something that really, something like the mean. The mean's great because it's something, intuitively it feels good because you calculate it, right? So intuitively it feels right because you've calculated something. But it's also something, because there's been these calculations, you can make comparisons between two things. So that's helpful. So the average amount that the data are spread out. Why don't we do the average amount of data are spread out? Let's do the average amount of data are spread out. Sounds like a plan. Okay, so that's what I did here. So we know the mean is 13, and I'm looking, looks like here, yeah, we got 1 minus 13, 5 minus 13, 9 minus 13, 20 minus 13, 30 minus 13. So what I've done is I've taken each number, that's with the more spread out one, was it 1, 5, 9, 13, 20. And I've summed the scores minus the mean, and I've divided by the number of scores. Okay, good. So I got negative 12 plus negative 8 plus negative 4 plus 7 plus 17, which is 0. Shit. So it turns out that's not good at all. I didn't want 0. There's not 0 spread, is there? This is a completely useless attempt at a measurement. It's intuitively pleasing as hell. Sadly, it sucks. This will, in fact, always sum to 0. In fact, the mean is a balancing point. That's what the mean is. It's a balancing point. So because the mean's a balancing point, you're going to have as much score on above the mean as you have below the mean. And because you have as much score above as you have below, it's going to sum to 0. If it doesn't sum to 0, you've done it wrong. All right. Right. Much mass on one side as there is on the other. If you think of those numbers like that, they have mass, like you can kick them. How do we get rid of negatives? Well, do you remember in about grade 7 when your teacher taught you about absolute value and you said, I'm never going to use this? Now you are. So absolute value, it's just like, -4 and 4 both have the absolute value of 4. It's how far away something is from 0. So what we do is we're going to take the absolute value. So all we've done here, I keep pointing it with my finger, and I should show you with my mouse pointer here. The absolute value of the numerator, what we had before. So now instead of this being -12, -8, we get 12 plus 8 plus 4 plus 7 plus 17, which should equal 48, assuming I did that right. Yeah. Divided by 5, which gives us 9.6. Hey, a number. This looks like something we could use. And what would it be for the other one? Well, it's 2 away, 1 away. So the other one's going to be 2 and 1 is 3, 3 and 3 is 6 over 5. So that's 1.2. Oh. Okay. That seems like it might be a thing. The mean absolute deviation looks like it's useful. So it seems cool, but it's not. For our purposes, the mean absolute deviation is just not that useful. It is not completely useless. It's completely useless for the kind of statistics we are going to do. But you'll often hear people say it's useless completely, and it isn't. It's actually a useful quantity. It just isn't something that's used a lot. So it's actually useful. It's just in the type of stats we do, it's a dead end. It doesn't get us anywhere, which is too bad, because it's very intuitively pleasing, right? It's extremely pleasing. Right? The intuitive appeal here is huge. Like, it just makes sense. Like, oh, that's great. But nope, it doesn't help us in any way. All right. Questions at this point? Does anybody have anything they want to ask? Okay, I'm not surprised you have a lot of questions. This is stuff you've seen before, but it's nice that you feel pretty up to date on it. That's good. There has to be a better way. Of course there is, or we'd stop the course. And I've got a lot more slides. So it's clear that we're not done yet. So there has to be a better way. And there is. The other way we can deal with this is, how do we get rid of these negatives? The nattering nabobs of negativity. Not many of your other profs make Spiro Agnew references. Some of these are just for me. So we're going to square the deviations, because if you square them, those deviations, those x minus x bar, -4 times -4 is positive 16. So we're just going to square them, and then we're going to get positive numbers. Yay. So it's like, well, -9 squared is 81, for example, just like 9 squared. So that's what we're going to do. And that's where, and you know that this is called standard deviation and variance. That's what we're going to get here. So this is better. We got here, so 1 minus 13 squared, 5 minus 13 squared, 9 minus 13 squared. So that's going to be 144, 64, 16, 49, and 289. Yes, 289. There's a thing when I was young, we had to learn all the squares of numbers up to 25. So you could do things like this quickly in your head. Of course, when I was a kid, I'm the same age I'm probably older than some of your parents. which makes me feel old. So stop saying it. It wasn't your fault. I brought it up. I've got a lot of personal problems. But anyway, so here we are. We've got a number that looks huge, doesn't it? 112. The mean was it 13? It means 13. How in the hell do we get, oh, we squared it. Well, we have to do something about that now, don't we? So they're squared. So let's put them back in the original units. It would be like if these were heights, suddenly you've got areas. It wouldn't make any sense. So we just got to take the square root, right? So let's take the square root. Square root of 112.4 is going to be what? About 10. I'm not looking at the thing. I'm trying to do this in my head. 10.8, am I right? 10.6. So about 10.6. Well, not about, it is 10.6. I mean, I clearly rounded here, but yeah, about 10.6. Okay. There's another thing we learned when I was in elementary school, how to take square roots in your head. I don't know why we learned those things, but it's a nice party trick. There's a problem here, and you know the problem. The formula I've shown you so far has n on the bottom. N is the number of observations. And I know that just makes sense. I'm well aware. I'm aware. This sucks. Because it should just make intuitive sense. It's supposed to be n minus 1. We want something that will be an unbiased estimator of the same quantity in the population. An unbiased estimator is something that, now this should not surprise you, that overestimates as much as it underestimates. Okay. You know that a sample is a subset of the population, right? And if I taught you 2126, and I think probably if Dwayne taught you that, that's the definition you were told. A sample is a subset of the population. We want to estimate the population parameter, for in this case, variance. But we don't have the population parameter because if we had it, we wouldn't have to estimate it. What we have is the sample statistic, right? So we want a statistic. It's never going to get it, well, sometimes going to get it dead on, but usually it's going to underestimate or overestimate. We want to have it underestimated as much as we overestimate. Right? Okay. So the population parameter variance and the standard deviation have big N on the bottom. Standard deviation, for me, it's just it's the square root, right? I read bottom because I always forget that I always have to go in my head, numerator, denominator, numerator, denominator. The other one I remember from elementary school is for less than and greater than signs. The alligator's mouth always points towards the biggest piece of food. It was taught to me by my grade 3 teacher, Mrs. Hoppamaki. Whatever happened to her? She was awesome. She used to trade hockey cards with us at recess and before class because she had kids and they had hockey cards, so she'd trade with you. God, she was a good teacher. I got really lucky. Had some really good teachers in school. Sample statistics used to estimate these things use n minus 1. Okay, they don't use big N. They use n minus 1. If they had n, they would actually underestimate the population parameters. They'd be too small. The nice thing is we know how much they would underestimate it by. We know that through math that I don't want to go through. Okay, so it's, you know what, go to grad school or take a math class in statistics. They can teach all about it. For our purposes, we don't care. So our sample statistics then look like this. S squared equals the sum of the x's minus x bar squared over n minus 1. And s is the square root of s squared. Now, technically, There should be an index here going n equals 1 up to k, but I decided to just leave that out because it just makes things more complicated for most people. And I think you know what this means. And this is just to be a shorthand so you understand things. That's why one does this, right? Questions so far? You good so far? Yeah? Okay. So in our case, then, here we are. Blah, 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 1 minus 13, 5 minus 13, 9 minus 13, et cetera, et cetera. So we get all this, and we take the square root of that, and we get 11.85. So it's not 10.9 now, it's 11.85. 11.9. Good stuff. So for the population, oh, no, they're not S's here. These are sigmas. Sigma squared and sigma. This is where this mathematical notification. I almost, I just did. Mathematical notation. Sorry about swearing there, but I got really frustrated. So this is a small sigma. This is a large sigma, a capital sigma. A small sigma, lowercase sigma is for this. And an uppercase sigma, that's these, is for a summation sign. I know it's annoying. It's also life. Also, look, hey, mu instead of x bar, because for the population parameter mean, we use mu. A capital N and a capital X as well. Okay. So we're estimating these with our sample statistics, which I keep forgetting. You push there, dummy. Okay. So S squared approximately equals that. Sorry. Yeah, that's right. And S approximately equals that. Okay. Good so far. Questions? Okay. How are the variance and standard deviation affected by extreme scores? So 1, 5, 9, 20, 30, this is our running example here. And the standard deviation there was 11.85. So let's throw in a new number. And I just picked this out of nowhere, and it's 729. Great. So now our new set of numbers is 1, 5, 9, 20, 30, 729. Our new mean is 132.3. Went up, eh? Before it was 13. And our new variance is that 85,000? I think so, eh? 85,555.067. Just trust me on that. I calculated that. Assuming I did the arithmetic properly, that's the right answer. Our new standard deviation is 292.5. I think we can say with some clarity then that the mean is affected by extreme scores, and then therefore so is the standard deviation. Right? So therefore so is the standard deviation. Okay, questions? Okay, whoa, that's slow. How can we use this information to our advantage? Like, how can we use it? The coefficient of variation. What's the coefficient of variation? So let's look at this. These are some data collected by Katz et al. In 1990. And we have two groups. One group studies and gets a percentage of 69.6. This is on, I think, an intro physics test, but I may be misremembering this. And their standard deviation is 10.6. Another group doesn't study, and their mean is 46.6 with a standard deviation of 6.8. Okay? You good? Okay. One could make a weird conclusion here that there's more variation with studying. Look, The variance here is the standard deviation, sorry, is bigger here than it is here. Much bigger. Why would there be more variance when, because you would expect people here are guessing more, right? When they don't study. So shouldn't there be more variation here, or maybe the same amount of variation perhaps? But you could conclude here that there's more variance with studying. So there's more chance of you doing poorly when you study than if you don't study. Excuse me? That seems wrong, doesn't it? Okay, let's look. The coefficient of variation is 0.152 and 0.146. The coefficient of variation, by the way, is just a quantity. Take the standard deviation divided by the mean. So 10.6 divided by 69.9, 6.8 divided by 46.5, we get very similar values there because the mean, the standard deviation and the variance depend on the mean, right? The standard deviation and the variance depend on the mean. So let's take a look. I mean, let me just go over here. Grab a different one. Let's do that. So if we take a look at our the formulas here for, so we've got, whoops, for S squared equals this okay. Now think of this as, so the sum of the x's minus x bar squared over n minus 1. Okay, so if this is the case, all else being equal, what happens if we make this thing bigger? That means we make the numerator of the fraction bigger, which makes the value bigger, right? So if we make the numerator of the fraction bigger, now the value is bigger. This whole thing. So as x bar increases, right? S squared increases. And if you want to get really mathy, the limit of s squared as x bar approaches infinity is infinity. So the bigger x bar gets, if this made sense to you, this thing here that I just said, that's great. If it didn't, don't worry about it. This is just a mathematical way of saying as this thing gets bigger, this thing gets bigger. Okay. Questions on that? Does that make sense? So this is something we have to always keep in mind when we're dealing with variances, standard deviations. Okay. There. That and good. So whoops, let's do that. And I got to quit this share here. And, look at that. I didn't realize it would do that. That's actually very cool. Okay. Do that. And I'm going to put that away. No, not like that. Stop share. There we go. Okay. I can pull this back up just in case anybody has any questions here. So go back to there. And where did it go? You know what? It might not be a bad time to stop for now, actually. It might not be a bad time. So, yeah, you know what? Does anybody have any questions? I think this is not a bad place to stop. We did a lot in one day here, so I know it's a little bit short, but there's nothing wrong with that. Questions? Who's got questions? You good? Well, you know what? We will continue talking about this on Tuesday. So take a look at the stuff in the book. Play with SPSS a little bit. get some data. Just, you could take any set of data. There is an assignment you can start working on. Get any set of data, throw it into SPSS and do that. All right. Any questions?
I have a question.
Don't apologize. It's my job and everything. What's up?
Okay. I know you mentioned the program JASP. Is it the same as SPSS? Because
No.
I know I emailed you earlier saying SPSS doesn't run with Chromebooks, so can I use
right.
JASP instead?
I don't know if JASP can run on a Chromebook. PSPP will, but I don't know about JASP. JASP is actually really cool, but you need. Wait, look. If only we had all of the world's information at our fingertips. Let's look. Chromebook installation, JASP. Ooh, look at that. Free and user-friendly. It looks like you can. All Chromebooks that came out in 2019 or later explicitly support Linux and therefore allow JASP to be installed. So here's a link. And I will share the link in the chat here. Yep. Okay, so I'm just going to throw this into the chat. And you can take a look at it. Okay, so right there, we're going to go paste. JASP is different than SPSS, but it's really super powerful. It's super powerful. It's also something that is used. There's a whole community that uses JASP. So it's something you could use. You'll have to learn how to use it kind of yourself, though. I've played with it a little bit. It's different than SPSS, I'll say that, but it's useful. Yeah, good question. Okay. Other questions? Anything else? Anything at all? You all good? All right. On that note, I will see you next Tuesday. I'll see some of you in an hour and a half in NeuroFarm. Thanks, everybody. So we're going to go like that. So let's all acknowledge that. All right, so this is where we left off last time, and it's the idea that I talked about this last time. I'm just going to move a window that you can't see right now. Okay, so how do we use this to our advantage? And I talked about this last time, the idea of the coefficient of variation. And these are data collected by Katz et al. 1990, and Katz is a Facebook friend of mine from Western. When he was a prof there when I was a postdoc. So people are given two tests, two groups. One group studies, and their mean is 69. And their standard deviation is 10. And the other group, they don't study. Their mean is 48 or 46, sorry, and their standard deviation is 6. And you could make a very strange conclusion here. And that conclusion would be that studying makes your marks more variable, right? Because look, the standard deviation is bigger here than here. That would be a very strange conclusion, wouldn't it? It just seems odd. Why would it be that studying makes your marks more variable? I don't know. In fact, that seems counterintuitive and bizarre. So if you take a look at what's called the coefficient of variation, that's the CV. This is another one of these exploratory data analysis techniques. We end up with 0.152 and 0.146. Coefficient of variation basically is just the standard deviation divided by the mean. And I've literally used this. I used it last year when a student had some issues with her, questions, I shouldn't say issues, with her data for her honors thesis. And we looked and I said, oh, let's just do the coefficient of variation. We looked, oh, they're almost exactly the same. The reason that, and this is where we left off last time, the reason that the standard deviation here is bigger than this one is simply because mean is in the formula, right? So when you look at something like, where are we? When you look at the mean, oops, where are we here? Oh, I didn't turn my pen on, there we go. So when you look at the formula rather for standard deviation, which is the sum of the x's minus the x bar squared over n minus 1, that's variance, but it's the square root of that. One of the key things in here, is the mean. If the mean gets bigger, that means this whole thing gets bigger. If the numerator of a fraction gets bigger, the number gets bigger. So the only reason here that we have this weird result where the standard deviation is 10.6 for one and 6.8 for the other, it's basically simply because we have different means. We have a much bigger mean in the study group than we do in the no study group. Does that make sense? Everybody okay? Any questions I can answer about that? All right. So as I said, that's where we left off last time. Right. So there's a couple of key things. Now I'm just sort of throwing out stuff at the end. So of the lecture, though, again, I want you to, this is where it might get tough-ish. Boy, that came up slowly, eh? Remember, we want to learn about populations, not samples, but we don't have populations. If we had population data, we would not have to get samples. Like if I actually knew, let's not go with me. Let's go with, let's say there's an election. There will be an election in Ontario in June. There will be an election, could be a federal election anytime. Well, the parliamentary system means there could be a federal election anytime in a provincial. But anyway, there'll be a federal election probably in 2.5 years. There will be a provincial election in June. We know that. So if that's the case, we're going to see political polls, right? And you're going to see confidence intervals, plus or minus this many percentage points, 19 times out of 20, confidence intervals with a P level at the end, beautiful, that everybody's going to misinterpret. So if the pollsters, if the pollsters could actually get the population data, if they actually knew how everyone was going to vote, which is what we get on election day, they wouldn't have to collect samples of 1,536 people, right? But so they're trying to make inferences about a population, but they can't measure the whole population. The only people that can do that, who have the money and the time and the inkling, is the provincial government or the federal government or whomever's running an election, right? So we really want to know about populations. Samples we don't care about on their own. We care about, is the sample unbiased? Is the sample not different from the population? That's what we want. That's what's important. So we estimate population parameters using sample statistics, right? So for example, we've got things like, whoops, it just spun on me a little bit. Let's change color. Let's go to black. Out of the red and into the black. I know it should be blue. It's also a Neil Young reference that I don't think any of you are getting. So if we've got a sample statistic like X bar, we want that to estimate mu. If we've got a sample statistic like S, we want to use that to estimate sigma, the population standard deviation, right? So we're trying to estimate the population parameters, that's these guys here, which we usually use Greek letters, with sample statistics, that's these guys here. Now, the important thing here is that as a rule, sample statistics, as a rule, population parameters are unknown numbers that describe a population. Now, sometimes we eventually can know them. An election tells us the actual literal number of people who voted NDP or Liberal or Conservative, or let's pick a minor party, Marxist Leninist. So we know who's voting, not who, but that would be bad, but we know how many people voted in a certain way, right? That's a population parameter, and we can, in very specific, very certain circumstances, we can get that. But can we actually know? Let's think of a psychological experiment. We're counting the number of words you recall from the list I gave you. Can we actually know the average number of words a human can get? Well, the answer to that is obviously no. So we estimate it. So the number itself, these numbers are unknown. Population parameters typically are unknown. Sometimes you can get a theoretical number, but usually they're unknown. The sample statistics, however, are known. We calculate the sample statistics. And the way to remember it's sample statistic population parameter, SSPP. That's how I remembered that when I was an undergrad. So we're trying to estimate population parameters with sample statistics. And what we want are what's called unbiased estimators of parameters. We want unbiased estimators of parameters. We want them to overestimate. Did I just say we want them to? I think I did. We want them to overestimate. I can't speak. I've lost the ability. It's sad, really. We want them to overestimate. The sample statistic should overestimate the population parameter as much as it underestimates the population parameter. Sometimes it's going to be right on, but usually it's not, right? Even the best political polls. Who would I say has the best percentage political polls right now in Canada? Nanos or Ipsos are probably, or Ecos are probably the best. They're still wrong, because they don't have the wherewithal to measure the whole country or the whole province or whatever. So they still make mistakes, but they want them to overestimate as much as they underestimate. And that's what we want too, right? Any questions so far? Okay. I see you all in the black boxes on the side of my screen. I'm really okay with it. Look, if you don't want to show your face, that's fine. Show yourselves. Anyway. So to get an unbiased estimator, the beautiful thing about unbiased estimators, but the mean is the X bar is an unbiased estimator of mu. Woohoo! So that's great. Now we have a problem. Standard deviation. Remember I said we divide by n minus 1, and I talked about how it's if we use n minus 1 as the, let's see, numerator, denominator, as the denominator, we get an unbiased estimator of the population parameter. If we use n, we don't. We get a biased estimator. The beautiful thing is we actually know how much it biases it, and it biases it by n minus. So we can, if we take n minus 1, it's not going to be biased. We don't have to worry too much about the math behind that because it's beyond the scope of the course. But I can tell you that what you're dividing by there is the number of degrees of freedom. The math comes out when you do the math behind this, that's all calculus. It tells you that when you divide by the number of things that you have fixed minus 1, values you have fixed minus 1, then you get an unbiased estimate. So let me just show you what I'm talking about here. So let's go back to, where are you? Share content, whiteboard. Yes, I know that's going to change that. Okay. So if we've got a case where we have, what was the thing we were using, but it was always 11, 12, 13, 14, 15. It was 5 numbers, right? So if we have 5 numbers, in that case, so it was, let's see, 11, 12, 13, 14, and 15. Okay, we got those 5 numbers. And the mean of that is what? 11 and 12 is 23. 23 and 13 is 36. That's then 50, 65, 65. So the mean equals 65 divided by 5, which equals 13. Okay. The numbers don't know where they come from. All this thing knows, that's this. Let's just do it for variance right now. All this quantity knows is that we have fixed this value at 13 because we put that in there. The rest of the numbers doesn't matter. But there's a restriction because we've fixed this value, X bar. Because we fixed that, there is a restriction we've put on. And that restriction is that these 5 numbers must sum to 65. They must, they can't not, because the mean is going to be 13 and n is 5. So if that's the case, we can have any set of numbers at all. So like, I don't know, let's just pick some numbers. 4, 2. That's the ugliest 2 I've ever seen in my life. 2 minus 3, 7. Okay, now we have to, this final number is now fixed because 4 and 2 is 6 minus 3. So that's 3, and 7 is 10. This has to add up to 65. What's this final number have to be? Anyone? Anyone? Somebody say what the number has to be. I'm prepared to sit here all day. It's got to sum to 65. 4 and 2 is 6. Yeah. Ooh, yeah. Go ahead.
55.
Yay! We have a winner. So that has to be 55. It must be. It can't not be. It's the only number it can be. Okay. It just can't not be. And we can do this. You could do this all day long. And I encourage you to, if you have a great deal of free time, to keep picking up 4 numbers. And if we were doing this in class, like face to face, I would do this 3 or 4 more times, and I would have you just picking numbers, and then people get clever and they go minus 600,000.216. You can still do it that way. You have to use that ridiculous voice, obviously. It always works. This number here is fixed. So we have a certain number of degrees of freedom. Okay. So we have a certain number of degrees of freedom, n minus 1. In this case, because we have 5 numbers, so if n equals 5, n minus 1 obviously equals 4. So we have 4 degrees of freedom. The beautiful thing is the math behind all of this, which actually is quite pretty. The math behind this says that the number of degrees of freedom is what you divide by, so you end up with an unbiased estimate. So I'm going to pause there and ask you if you have any questions I could answer, or perhaps questions I can't answer. You're good? Excellent. Okay, so let me, once more. Yeah, that's fine. We're going to do that. And we are going to go back to this. Where'd it go? I lost it. There we go. Okay. So the point here is then that we want to estimate population parameters using sample statistics. We're going to get a biased estimate if we use n as the denominator. Can you actually just see my brain going numerator, denominator every single time? So we're going to do that by dividing by n minus 1. So that's why you divide by n minus 1. The math behind it, which is really pretty math, if you're into calculus. But the cool thing is that it works. So we're trying to estimate population parameters with sample statistics. Okay, let's say we've got some numbers. And these are things that we're going to do to a sample statistic. So let's look at the first one here. The E, when I say E, that and something in brackets, that's just expected value. The expected value for something, I'm going to move my keyboard out of the way so I can lean on my desk because I don't really need my keyboard. The expected value of a statistic is the long running average you would get. If you calculated that sample statistic in an infinite number of times, you would get whatever the expected value is. So the expected value of the variable X. So a variable is just, it's a number, and it can change values. Okay. The expected value of X is X bar. So the expected value of some number that can change is its average. So if you add a constant to that, so that's plus K. Now K is going to be the same number all the time. Now the expected value of X, that's a variable, plus K, a constant, is X bar plus the constant. Okay. So think about this. Let's make this a little bit more realistic or concrete, not realistic. So let's say the average, let's say X. So our X variable here, our X number, our X variable, let's say that's the score on a test or in a course, even though let's make it a course. That's your final mark in Psych 3256. The expected value of that number is its mean. But let's just say, and this has never happened, that the average in the course was like 50. That's a bad year. And if the average in a course that I've taught 27 times that usually has an average in the very high 70s or low 80s, because people are in the honor stream and everything, and they tend to be very interested in this stuff, interested in that. Well, interested isn't quite the right word, but they take it seriously. Tend to do well. So if they already got 50, I was like, that's on me. That's going to be on me. That's not on you. That would be on me. I got to do something to that. So if I took all the scores and added on a constant, so if I said 50, the number really should be at least 75. If I added on 25 to everybody's score, the new average is going to be 75, isn't it? 50 plus 25. Any questions about that? Does that make sense? Because that's all this says. The expected value of a variable plus a constant equals X bar plus the constant. Okay, so the variance doesn't change. Or sorry, the expected value doesn't change. Does the variance change? This is where you have to do a little bit more thinking about this. This is a little bit less intuitive for a lot of people. The variance of X plus K is still just S squared sub X. It's still just the variance. Now think about this. If I've got a score, a set of scores, and so it's a distribution of scores, that would be all your scores in Psych 3256. And I moved them all over because I added a constant. Does that change how spread out they are? No, it does not. So it does not change how spread out the scores are. So the variance of X plus a constant, so a variable plus a constant, is still just the variance of that variable, S squared sub X. Okay. So far, are there any questions? So if we had a distribution, if we had let's just, again, do this with this. So if we had, let's say this was some class, as I said, and the mean was 50. And if I added 25, so now the K here, if I added 25 to all scores, the new mean would be 75. But let's say the variance was, I don't know, 100. If I add a constant to that, the new variance is still 100. Okay, sorry, the new variance, that's a dummy. The new variance is still 10. The variance is still 10. Why is that? Because it doesn't change anything. So if we look, or I guess that's just a tautology. Why doesn't it change anything? Okay, we've got a distribution. Let's change the color we use. Let's go with green. That's exciting. And then I just move them all over to here by adding numbers to them. It shouldn't change the distribution. It shouldn't change how spread out they are. In fact, it doesn't change how spread out they are. Okay. questions on that? You literally don't have any questions on that. Okay, that's good. Let's see what happens what if we take the expected value, of a variable and we multiply it times a constant? The rare times when I have actually changed people's grades, it's never in this class because this class is extremely consistent. It does happen now and then when I've taught intro. I don't teach intro psych anymore. I'm pretty sure that apartment thinks I frighten people in first year, so I don't teach them. And I'm glad not to teach first year intro psych. We have perfectly capable people of doing it in the department. I mean, none of them are as good as I am, but they're pretty good. So it has happened when I've taught it in the summer, and that's been I haven't taught a summer course in a long time as well. In the summer, things go really fast. If you miss one class, it's like missing a week of school. You've probably all taken, or maybe some of you have taken summer classes, right? It can be a real pain because if you do miss a class, it's like you've missed a week of school, right? And one year, we taught the course. It was me and Paul and Dwayne taught it at 4 times the speed. We taught it over in 3 weeks. So if you missed 2 classes, it's the equivalent, or if you missed a week, it's like missing all of September and half of October. Okay. So, but if you miss a class, you're going to be in trouble. What can happen in that case is test marks on the first test can be pretty low. So that's one time when I have adjusted marks, but I don't tend to add a constant. Because think about it. If you got 50 and I added on 25, your mark has gone up by 50%, hasn't it? Right? Because half of 50 is 25. So you can watch graph from 50 to, wow. If you got 100, and now you got 125, which fine, that seems impossible, but whatever. Your mark's now only gone up by 25%. I have actually rewarded people who have done more poorly more than I've rewarded people who've done better. That seems literally exactly the opposite of what I should do. So typically what I do in these situations is I take a look and I say, okay, what should the average be? And frankly, for courses like intro, where I've taught it not so much recently, but a lot in my career, if we took a course like 2606, Introduction to Behavioral Neuroscience, for example, which I've taught a lot, I know what the average should be on the first test. It's 68.2 with a standard deviation of 8.2. And I'm serious, like that's how much I know that course when I teach it. So I might look at something and say, look, the average is, I don't know, it's 50. That seems too low. It should be 60. And in intro psych, the first test, the average is usually should be 60. Right? Remember intro psych, your first class? I talked about this last time, I think. Hey, it's your first test you've ever had in university. Oh, look, it's worth 30% of your final grade. It's at the end of September. Have fun with that. So people get a little freaked out. So even in the regular year. So if we're going from, say, and I look and I see, oh, the average is 50, it should be 60. What would I multiply 50 times to get 60? That's me asking you to tell me. Anyone? It's arithmetic. You should be able to do this arithmetic. Come on, guys. Well, if I multiply it times 1.1, it would be 55. Multiply times 1.2 would be 60, wouldn't it? All right. Okay, so I would multiply times 1.2. That then gets me an average of 60 because the expected value, I pointed at the screen with my finger, the expected value of x times k is x bar times k. Beautiful. So everybody multiplying times 1.2, we got a new mean of 60. Yay. The variance. This gets a little weird. in a way, but when you think about it, it actually shouldn't. Variance is a squared quantity. So let's say our variance was 10 on this mythical intro psych test, where we have so you get a variance of 10 and a standard deviation then of root 10, right? Square root 10, and a mean of 50. So if our variance was 10 and we multiply times 1.2, right? Our new variance is still, so we get S squared is 10. And K squared 1.2 squared is 1.44. Is that right? Yeah, should be, because 12 times 12 is 144. Yeah, 1.44. So it's 1.44 times 10. So it's 14.4. The standard deviation is just going to be S times K, because the standard deviation, which is what this is going to be here, is always the square root of the variance. So it's going to be root 10 times 1.2. So remember, when I'm adding a constant, I'm not changing how spread out, that's the variance, how spread out the value is, or sorry, the distribution is. And when I multiply times a constant, of course, I'm changing how spread out it is. When I multiply, does that. Do you have any questions about that? You're sure you understand that? Do you have any questions? I'm happy to answer them. They pay me and everything. You good? All right. This may take a lot less time today than I have scheduled, which is fine by me. So exploratory data analysis is easy to do. You just basically go, if you've played with SPSS yet, and I know some of you have, one of you has already handed in their assignment that's not due till a week from Thursday, which is great. Way to go. Doing exploratory data analysis on a computer is trivial. It involves getting a data set into something like SPSS or JASP or whatever, or R if you're nuts, and pointing and clicking, or if you're R, writing some code. It's really easy. And it's simple to do. You can get box plots and stem and leaf plots and all kinds of summary statistics. It's trivially easy to do. And I think it's essential. The number of times I have looked at data and thought to myself, now I know what happened. And as I said last time, my PhD advisor used to say, statistics are there to prove what you already know. You can look at the data and say, I'm pretty sure I know what happened. Let's make sure that the stats back it up. Right? But I should be able to, just through looking at charts and graphs, I should be able to completely understand what's going on. Or not completely is a little strong for most people. But once you get a feel for your numbers, you should have a pretty damn good feel for what literally happened. But a lot of people overlook it. So I think it's essential. I think because it also allows you to spot outliers, spot just crazy values, like coding errors. So sometimes outliers are from literally because the person comes from a different population. I talked earlier, well, last time, if you're watching this on a video, this is earlier in the video. If you're watching this, or if you're thinking about this last time from last class, I mentioned a case where there was some data collected on cigarette smoking, and the data set said that somebody smoked 400 cigarettes a day, which you can't do. Well, you can probably, but you die pretty quickly. Nobody smokes 400 cigarettes a day. You also would have to be infinitely wealthy. So nobody's smoking 400 smokes a day. It's probably 40. It's probably a coding error. That's a way to spot it. Now, do you know it's a coding error? You might be able to go back, look at the surveys you put into your into SPSS or Excel or whatever you're using, and say, oh, I just looked. I see this is survey number 7, and I just hit the 0 twice. Okay, I can change that. But sometimes it might be that the person actually said 400. In that case, they're probably very few people do this when they fill out surveys and questionnaires, but some people act like jerks. So they make mistakes on purpose. If that's the case, don't use any of their data. It also might be, and I talked about the same data set, someone says they started smoking at 4. That's pretty young. Maybe that person doesn't belong to the same population you're trying to talk about, because that's a level of smoking that most of us aren't really used to, even back at the height of cigarette smoking. You know, the 50s and 60s, the 70s, people didn't start smoking when they were 4 usually. 14, sure. 12, 10, but 4 is pretty young, right? So in that case, if they say they're smoking at 4 and it says that in the questionnaire, you probably just want to remove their data, because either they're messing with you or they're really not part of the population you're actually interested in. They're part of a population of super smokers. Yeah. So do exploratory data analysis. It's easy to do. And I think it's pretty critical to do it. And I don't think enough people do it. And I can tell you that every time my honors thesis students come to me with their data, I say, okay, let's just look at some pictures first. Let's look at some graphs. Let's look at some numbers before we get into do analysis, variance, regression, or whatever you're using. Right. And the other day I was talking to my daughter who's looking at some data for a PhD thesis. And that's what we were doing. We were just looking, because she said, can I look at, can you help me? I'm sort of stuck. Let me look at this. We looked at it and I said, well, yeah, and she's done exactly that. We looked at it and said, we know what happened. Now let's find out, how do we analyze this? What's the best way to do this? But we can tell pretty clearly what happened by looking at some graphs, right? All right. All right. Do you have any questions at all? Because I mean, this literally is all I'm going to do today. Well, not all. I have another class and everything. But do you have any comments or questions or anything you want me to clear up?
I have a question.
I have answers.
Perfect. So for the degrees of freedom, because
Yep.
it has one fixed number, it's n minus. But if there was 2 or 3 fixed numbers, it'd be n minus 2 or n minus 3.
That is correct.
Yes.
Yes.
Okay. Just double checking.
No, you've nailed this. That's exactly right. So a lot of people think that degrees of freedom are always n minus 1. And in fact, when you're in 2126, I don't know if I can't remember if I taught you 2126 or not, but a lot of times when you're in 2126, you get the idea that degrees of freedom, it's n minus 1. And it is for a lot of things, for variance, standard deviation, etc. It gets a little more complicated. So you're right. The more general way to look at it is it's the number of fixed values minus, sorry, the number of values minus the number of fixed values. A very general definition of degrees of freedom is the freedom numbers have to vary. So it's the freedom numbers have to vary. It's a weird thing to think of, that numbers are free to vary, but you've got to, and that's one of the hardest parts about when you get into the sort of somewhat theoretical stuff about stats, is that numbers don't know where they come from. They can be anything. Some will become the president. I don't know what that means, but so they can be anything. But sometimes there's restrictions put on them. In fact, there's almost always restrictions put on them. And we always have to take that into account. And again, that's because of the calculus behind all this stuff. But you're right. So if there were 3 fixed numbers, it would be, say, n, that's the number of numbers, minus 3. If those numbers are the number of groups, and there's going to be cases very soon in this course where we do degrees of freedom, and it's about the number of groups in an experiment, and there are k groups, it's going to be k minus 1. And you say, well, Dave, they're just the number of groups. Yeah, the numbers don't know that. The numbers are ignorant. They are not aware. So if you just generally think it's the number of values that can be arbitrarily assigned or the freedom numbers have to vary, those are good definitions of degrees of freedom. Excellent question. Other thoughts or questions? Sounds like whatever's being microwaved in the kitchen still. All right. Okay, I'm going to stop the recording because why keep running it?